The ideal gas law. Okay, so let's just remind ourselves of a few of the characteristics of gases. So remember that they don't have a fixed volume or a fixed shape, so they expand to fill the volume of the container and take whatever shape that is. And we describe them in terms of four macroscopic observables, which are pressure, temperature, volume, and moles of gas. Now, we went through the early gas laws, and they described these macroscopic observables relative to each other, but they didn't combine it all into one big picture. And so we looked at Boyle's law, which related the pressure and the volume, and the temperature and moles of gas were held constant. Charles' law related the temperature and the volume, but kept the pressure constant and the moles constant also. And then finally, Avogadro's law just tells us that 1 mole of any gas at standard temperature and pressure will take up a volume of 22.4 liters. Okay, so let's continue developing this reasoning for the ideal gas law. Now we want to put all of these laws together into one ideal gas law. That's where we're going with this. So we're going to use Boyle's law. The pressure of the gas is inversely related to its volume. We're also going to add in there Charles' law, where the temperature of the gas is proportional to its volume. And then finally, Avogadro's law, related to the volume of the gas to the moles of gas. So if we put all these guys together, then we're going to get something that looks like this. Okay, so we have the volume is proportional to the moles of gas times the temperature divided by the pressure. Okay, now you don't need to be able to do that. All right, we're just going through this and seeing where it came from. But we do need a proportionality constant to be able to use our relationship for calculating volume, moles, temperature, or pressure. Okay, so you can see right now we know that they're proportional, but we don't know, we wouldn't be able to get an exact value for any one of these, even if we had the others. Okay, so the gas constant R represents this proportionality. Okay, so this is a constant. All right, now R can have different units. All right, so we're going to, keep ourselves corralled with this particular version, but there are other versions of R with different units, and they all represent the same type of thing, okay? But for us, we're going to use 0.08206 liters, atmospheres, mole, Kelvin, okay? So for all of our ideal gas law problems, we need to make sure that we first convert all of our units into liters, atmospheres, moles, and Kelvin. Okay? So that's always going to be the first step whenever you see an ideal gas law problem. All right. So now that we have R, we have the volume is equal to R, which is our proportionality constant, times the moles of gas times temperature divided by the pressure. Okay? Now if we rearrange that a little bit, then we're going to get PV equals nRT. All right? So this is the ideal gas law. All right, and this, I've heard some students call it PIV-NERT. Okay, so this is PIV-NERT. Okay, and now again, you don't need to be able to derive the ideal gas equation. We just went through it so you'd see where it comes from. Okay, so let's do an example problem. All right, using the ideal gas law. Okay, so when we heat solid calcium carbonate, it decomposes into calcium oxide and carbon dioxide gas. Okay, and that's according to this reaction below. Okay, so here's our calcium carbonate. We're going to heat it up, and we're going to get these two products. It's going to decompose or break up into calcium oxide and carbon dioxide. Now, we're going to heat a small sample of this calcium carbonate, and we're going to collect carbon dioxide gas in a 125 milliliter flask. Okay, and when we measure the pressure of this gas, then we're going to find out that it has a pressure of 1.95 atmospheres at 45 degrees C. So how many moles of gas were produced? We want to be able to figure that out. And let's just take a quick second and just look at what we're given in the problem and see why we're going to use the ideal gas law as opposed to one of the other gas laws that we talked about earlier. All right, and one of them is, here's a volume. We're given a volume. Just one though. We're given a temperature. We're given a pressure. Okay? So we are given a volume, a temperature, and a pressure, and we're asked for moles. All right? So when you see something like that, when you see all of those variables in a question, then you're going to start thinking about using the ideal gas law. Okay? All right. So let's go ahead and look at what we're given in the problem. So we have the volume is 125 milliliters, okay? Pressure 1.95 atmospheres, and temperature is 45 degrees C. Now what are we looking for? We're looking for moles of gas. And so we're going to use the ideal gas law for this problem because we have pressure, volume, and temperature, okay? Now another thing that we need to do is convert all of our givens into the correct units for the ideal gas law, okay? And so temperature needs to be in Kelvin, and just remember you take the degree C, you add on 273 and you get 318 Kelvin. That's the conversion from degree C to Kelvin. And remember, for gas laws we always have to be in Kelvin temperature units. The volume needs to be in liters, so we're going to remind ourselves that there are 1,000 milliliters in 1 liter. Okay, so 125 milliliters is converted to liters is 0.125 liters, and the pressure should be in atmospheres, and fortunately for us, it already is. Okay, so now we are going to use the ideal gas law because, of course, we have our pressure, we have our volume, and we have a temperature, and we're looking for moles. So we're going to rearrange PV equals nRT, or we're going to rearrange PIV-NERT and solve for moles. Okay, so here's moles. And now we're just going to plug everything in, okay? All right, we're going to make sure our units match. We're looking for moles, liters, liters, Kelvin, Kelvin. Okay, so everything looks pretty good. Okay, so canceling out all of our units, and you can see that we end up with moles, all right? And when we go ahead and do the math, multiply on top, divided by these two multiplied together, we're going to get 0.0093 moles of carbon dioxide gas. And if we wanted to, we could go ahead and convert this to mass of carbon dioxide gas.